Well, antimatter is really interesting because when the universe was created, it's predicted that equal amounts of matter and antimatter should have also been created. However, there's a lot of matter in our universe. Everything we can see and touch and feel is made of matter, but there's not a lot of antimatter. And the reason that we know there's not a lot of antimatter is because when matter and antimatter come together, they will annihilate.
Welcome to a new episode of the PAM Talks. The PAM Talks is a student-led podcast showcasing the voices of researchers who are part of traditionally underrepresented groups in physics and astronomy. Each episode, we interview a new physics and astronomy mentor, exploring the universe through the lens of diversity. My name is Becky Booth, and I'm a PhD candidate in astrophysics from the University of Calgary, and I'll be hosting today's episode. Today I'm interviewing fellow graduate student from the University of Calgary, Abby Swadling. Abby is a master's student in particle physics. And I first met Abby when I was a TA for her second year undergraduate laboratory class. I'm really excited to be able to introduce you to Abby today as a proud former TA, but also as a bit of a super fan, because I think her research is honestly so exciting and interesting, and I can't wait to be able to share it with you. Abby's research is part of the ALPHA collaboration, an international collaboration based out of CERN, which is home of the world's largest particle accelerator and is located in Europe. ALPHA is focused on studying the properties of antihydrogen. And in this interview, you'll hear about how ALPHA is trying to detect particular spectral lines from antihydrogen to try to answer some of the biggest questions about how matter and antimatter are related. Coming up next, my interview with Abby.
Hi, my name is Abby, and I'm a first-year master's student at the University of Calgary, and I work with Dr. Friesen and the ALPHA collaboration. My research focuses on looking at some of the properties of antimatter.
Hi, Abby, and welcome to the PAM Talks podcast. So, you said that your research is into antimatter. So, could we start with defining that? What is antimatter?
So antimatter is similar to regular matter. It has the same mass, but it has the opposite electrical charge. So if you think about an antihydrogen atom, and we can compare it to a hydrogen atom. So a hydrogen atom is made of a single proton and a single electron. An antihydrogen atom will be made of an antiproton and a positron.
Okay, so antimatter is basically the same mass as regular matter, but has the opposite charge. And we know that all around us is regular matter. Like we have the periodic table, which is made up of elements which are regular matter. Can you have an anti-periodic table?
I suppose you could think about it that way. Yeah, theoretically, there would be the possibility to have an anti-atom corresponding to any type of atom.
So, like, that anti-atom would be made of all the same number of antiprotons and anti-electrons as the regular one, just opposite charges.
Yeah, exactly. You would expect to see the same number of components making up the anti-atom as for any atom, it would just be the antimatter counterpart.
Okay, so why should we be interested in antimatter?
Well, antimatter is really interesting because when the universe was created, it's predicted that equal amounts of matter and antimatter should have also been created. However, there's a lot of matter in our universe. Everything we can see and touch and feel is made of matter, but there's not a lot of antimatter. And the reason that we know there's not a lot of antimatter is because when matter and antimatter come together, they will annihilate.
So, annihilation, that sounds really dramatic. Can you explain what it means for matter and antimatter to annihilate?
So when matter and antimatter come together, when I say they'll annihilate, what I mean is they will explode. And these explosions will release energy, which can be in the form of light, which we would refer to as photons, which is just a discrete way of looking at light. And additionally, they can release some subatomic or smaller particles.
So, if there is an equal amount of matter and antimatter in the universe, we would just expect to see explosions everywhere.
Yeah, perhaps, or we maybe would expect that everything exploded a long time ago and there would be nothing.
Yeah, and I mean, I'm here and you're here. So obviously some matter stuck around. So that sounds like a really important question is where is the antimatter and why aren't we all exploded?
Yeah, exactly. That's kind of the motivating question for the research that I'm doing is trying to ultimately answer that.
So, how do scientists even go about solving that kind of problem?
Well, there's lots of different approaches that you can take, and there's many different groups across the world that try to investigate different aspects of this problem. The group that I work with, the Alpha Collaboration, is focused on looking at differences between antihydrogen and regular hydrogen. So the idea is that there are a lot of properties of hydrogen and antihydrogen that are predicted to be the same. So if we can measure these experimentally, then we can either prove that they're the same and support the current theory, or we can find some difference and potentially have a step towards explaining why there's so little antimatter in the universe. For example, a recent publication that the group made was looking at the effect of gravity on antimatter. So they produced a bunch of antihydrogen and then dropped it to see if it would fall up or down, just to see how gravity would impact it. And the idea was that if it fell down, it would follow the theory that is currently predicted. But if it went up, it would be a new discovery. Now, it did end up falling down, but the interesting thing is that now we have a physical confirmation for what was predicted, and we could repeat the measurement and obtain higher precision to get a value for the gravitational constant.
So, what I'm understanding is that we don't have a whole lot of antimatter. So, in the past, we've just had to assume things about its properties. And in science, we don't like to just assume things are true. We like to measure they're true and confirm that. So, it sounds like it was only recently we even found out that antimatter falls down.
Yeah, very recently, the paper that published that result just came out last year, so in 2023.
Okay, so the next step after the gravity result is to look at some of the other properties of antihydrogen to see if it behaves like we predict it to. What's the next property to examine?
Yeah, so my group likes to look at spectroscopy of antihydrogen. Spectroscopy is simply measuring if atoms absorb light or release light. So if they release light, it's called an emission, and if they absorb light, it's called an absorption. So what Alpha likes to look at is different emission and absorption of light by antihydrogen atoms to compare if it looks the same as a hydrogen atom. And the reason for these absorptions and emissions is that if you think of an atom, it'll have some nucleus, and then orbiting the nucleus will be some electrons or something. That model of the atom was sort of explained by Niels Bohr. You might remember the Bohr model from high school. So he kind of explained that we would expect to see electrons moving in circular orbits, and only certain orbits are allowed. So each of those orbits would have a different energy. And if you wanted to transition between one of those orbits, you would have to give off or take in some light. And each of those different energy levels will correspond to a different wavelength of light or wavelength of photons. So you'd see different colors.
It's really cool. It really feels like you're following in the footsteps of the giants of science, like Bohr, who was able to understand the atomic structure of hydrogen by studying its spectral lines. And now with antihydrogen, you have an opportunity to continue that work and really move science forward.
Hopefully, yeah, that's the goal of the Alpha collaboration. So hopefully we're able to achieve that.
Well, I'm really interested in your work and I'm quite excited to hear about the results. And I know with the gravity results, everyone from that collaboration knew for quite a while and they weren't allowed to say. Is yours going to be similar? Am I going to be waiting for the paper to come out and you'll be like, oh, I know the answer?
Maybe, yeah, it might be similar. It's exciting when we do these large scale experiments. We're working with groups of like 50 people, so we all have to keep the results a bit to ourselves until the paper comes out.
Well, we'll just work out like winking language. So pass me in the hall one day, two winks for yes, one wink for no.
Yeah, exactly.
Okay, and then we'll work out, like 15 winks for the exact wavelength of the spectral line that you detected.
Yeah, exactly. One wink for each significant digit.
Well, that's going to be a lot of winking. Okay, so as an astrophysics student, I spent a lot of time looking at different emission and absorption lines of hydrogen, mostly because there's just a lot of hydrogen out there. It's the most abundant atom in the universe. So I understand why hydrogen is important in my field of research. But for you, why choose antihydrogen? Couldn't you use any antiatom?
Well, antihydrogen is the simplest antiatom because hydrogen is the simplest atom. It has only a single proton and a single electron. So antihydrogen requires only a single antiproton and a single positron to form a stable antihydrogen. It should be possible to synthesize other antiatoms. However, so far, alpha has not done that, but in the future it could be possible. But for now, it's just because antihydrogen is the simplest antiatom, and that's what we're able to produce presently.
Yeah, that makes a lot of sense. Okay, so there's not just antihydrogen floating around. We've already talked about how antimatter doesn't appear to be very abundant around us. So, where do you get the antimatter from?
Yeah, so the Alpha collaboration is based out of CERN in Switzerland. And the reason for this is that CERN is able to provide a supply of antiprotons. So, since antihydrogen is made of an antiproton and a positron, we need to have antiprotons. So, how antihydrogen is made is you take some antiprotons from CERN and then you produce or you collect some positrons from a positron source, which is something like sodium. And then they come together, and through a bit of a complicated process, you can bring them together to form an antihydrogen atom.
And do you just get one?
Well, hopefully not. You need many antiatoms to perform an experiment. So we're always trying to create more and more and optimize the process that we use in order to be able to have more. So on average, we used to have about 10 to 20, and recently there's been an advancement. Now we can get around 60 on average consistently every time we bring antiprotons and positrons together.
Amazing how small a number that is, just like 20 to 60 atoms. And to be able to generate them, contain them, and know where they are, that's amazing. So, CERN is such a fascinating place. And I know that there's been like all sorts of concerns in the past with CERN, like, oh my goodness, are we going to make a micro black hole and explode the Earth? Now, antimatter explodes when it meets matter. I'm assuming that we're not gonna, like, explode the Earth with your antimatter experiment.
Oh no, we definitely shouldn't. It's such a small scale that the type of annihilations we're seeing, you wouldn't even if you were standing right beside it, it's it's in a trap, you wouldn't even know. It's so small. There's no risk of that really.
Yeah, so I guess on that note, how do you prevent the atoms from just exploding right away? 'Cause, you would think that as soon as you make an antihydrogen atom, it runs into some matter maybe on, like, the wall of whatever you're trying to contain it in. How do you keep it around long enough to do a measurement?
Yeah, so the amount of time that we can hold an antihydrogen atom in our trap is about 12 hours to a day, which is enough time for us to perform a relevant experiment.
That's way longer than I imagined. I was imagining like nanoseconds, but you've got like antihydrogen atoms just hanging out for the day. That's amazing. Okay, so let's go into your specific research a little bit more. You're measuring spectral lines of antihydrogen. Is there a particular spectral line that you're looking at?
Yeah, so in the past, Alpha has been able to do spectroscopy of certain spectral lines. So what I'm looking at is the next goal of the Alpha collaboration, which is measuring the Lamb shift in antihydrogen. So a bit of a technical term, that's the 2s and the 2p energy levels. So those are basically just labels given to two of the energy levels. Now, it was found experimentally that they did not have the same energy level as was predicted. And this little splitting that was found in the energy levels of antihydrogen is something that's very important in the current theories that are used to understand quantum physics and how atoms work. So, that small energy difference has not ever been measured in antihydrogen. So, that is known as the Lamb shift, and that's what I'm trying to measure for the first time in antihydrogen.
Okay, neat. So, how do you measure this Lamb shift transition?
Yeah, so the Lamb shift, like I said, is the difference between the 2s and 2p energy levels. So the difference between those energy levels is something that we can excite or we can apply light to cause a transition between those two levels in the microwave range. So it's not something that we can see. So what we do is we produce antihydrogen and we hold it in the trap. And then when antihydrogen is produced, it's going to be in a ground state. So it's going to have the lowest energy and it's going to be the most stable. So from that state, we can apply a laser to get it up to the 2s state, which is the first one that we're interested in. And then from there, we can apply our microwaves, which will hopefully cause a transition to the 2p state. So if we apply microwaves that are at the right wavelength that we think that transition will be at, and we are able to detect that the transition has occurred, then we'll be able to show that the Lamb shift is the same as it would be in matter, because we use the matter model to predict what wavelength of microwaves we need to send in. And if we didn't see any transitions occurring as we expected, then that could be an indication that something is different between regular matter.
And that would give more evidence for if hydrogen and antihydrogen share the same properties or not.
Yeah, exactly.
That's so cool. So, all this experimental work is being done at CERN. I got to visit CERN as a tourist a while back, and it really was incredible to see the scale of the facility. I think it's amazing that you get to go out there for your research. Now, you're in the first year of your master's degree, really just at the beginning. How did you get involved with this kind of research where you get to go out and work at CERN regularly?
Yeah, so I became interested in this field of research when I was in first year in one of my undergraduate physics courses. The professor of that course, Dr. Friesen, talked about his research, and it was really interesting to me. So later in my degree, I asked him if there would be any opportunities for an undergraduate to get involved in it, and he said there would be. So I worked on a project with him at the University of Calgary. And then the next year, I said I was still interested and I'd love to work more on this. And he was able to send me to CERN. So that was how I first got involved.
That's so incredible. I know that some of our listeners are just starting out, so maybe they're looking at starting an undergrad in physics. And to think just a couple years in, you could be just off to CERN doing experiments. How many times have you gotten to go out to CERN?
So far, twice. I went once in the summer of 2022 and once in the summer of 2023 for 4 months, both times.
4 months, that's not a vacation. That's like living out there. What is a typical day like when you're out at CERN?
Well, to explain a typical day, I'll explain a little bit how our collaboration works. So everyone has their own specific jobs, but everyone also has to work together to do things that benefit the whole collaboration. So we do these shifts. So you'll go in for 8 hours and you'll work with a team of people on something that will help everyone. For example, working to produce more antihydrogen. So a typical day might be like you'd go into work and I would work a shift, and then maybe I'd spend a few hours working on my project after, building some hardware or maybe running a bit of code. Like it totally depends on what needs to be done.
Well, that sounds like a lot of work. You're going in, you're in the lab all day. Is it just all work when you're out? Because you're in Europe. Don't you get to like eat chocolate and
Yeah, that's one of the big perks of the job is that since you have to be in Switzerland, which is really quite nice, we're able to go and do lots of things as a group. Lots of people in the collaboration will get together and go out and do things like go swimming or go out for dinner or go and see different things in Switzerland, which is really nice.
that's so cool. And you're meeting people from all over the world. So it's an opportunity to have friends from every country.
Yeah, exactly. It's a really great opportunity when you're over there because you definitely do work hard, but you also get to have the benefit of hanging out with lots of different people that you might not have had the chance to meet.
Yeah, I could see how that would be a really wonderful experience. And you're working with a lot of different people. How big is the Alpha collaboration then?
Yeah, it's roughly around, I believe, 50 individuals right now, and they're coming from all different universities, some in Brazil, Denmark, the United Kingdom, the Netherlands, and they all come together to work at CERN on one common goal. And it's really valuable to learn from people who have such different backgrounds than you. It makes it really interesting when you can come together and collaborate on one thing.
So, when you're part of a large collaboration like Alpha, some of the work is being done by the group as a whole, and some of the work is being done by individuals. What is your specific part of this project? Did you just dive in the middle when it was already planned, or where did you get to be part of it from the beginning?
Yeah, so measuring the lamp shift in antihydrogen is an effort of the entire collaboration, and I'm involved specifically in the microwave team, and I play a small role. I'm a small piece in the puzzle. So my first ever project, I looked at a little bit of pre-experiment work, kind of trying to look at whether this was possible. And then I was able to install some hardware that we were planning to use for the experiment, but ultimately did not end up using yet. We might use it one day. And then I was able to help plan out the process of running the experiment, planning what microwaves we're going to inject and how it's going to work.
That's really cool. And I love that you've had opportunities to work on this project right from the beginning, even investigating the possibility of the project in the first place and work on some of the hardware. I would love to be able to keep talking and hear all about your work, but I think we only have time for one more question. And this is something that I've just been curious about. So, you're working with really large scale equipment. I know from my experience in radio astronomy that these things are really expensive. Like the telescope I used was $18 million to build. And it's always a little scary to think about that when I'm the one in control of it. For your experiment, how much would you say it costs to do this kind of scale of experiment?
That's an interesting question. One of the big costs, which is interesting, is that in order to have everything working, we have it cooled to a very, very cold temperature. And we do that using liquid helium. Now, liquid helium is really expensive. If you look up the cost, it's nearly $20 a liter. And we use around 1,000 liters a day or more. So if you do the math of that, it's quite a lot of money.
That's incredible. Wow. So it sounds like even just for the cooling system alone, it costs around $20,000 a day to run. That's really a statement of how important this work really is, that people are willing to invest that kind of money into making sure that the project can run smoothly. Well, Abby, thank you so much for joining us on the PAM Talks. Even in the first year of your master's project, the work you're doing is so fascinating, and I can't wait to hear what you do next.
Yeah, thank you very much for having me. It was really nice to be able to share my work.
Okay, now remember, once you have your results, you see me in the hall, and 1 week for yes, 2 weeks for no.
We'll have to see.
The PAM Talks podcast gratefully acknowledges support from the University of Calgary Graduate Student Association Quality Money Grant Program.